A flashlight emits light in all directions. The sun radiates across a wide spectrum with waves that are completely uncoordinated. Even a bright LED produces photons that move randomly in phase and direction. A laser is fundamentally different. A laser beam is narrow, intense, nearly perfectly parallel, and composed of photons that oscillate in precise synchronization. It is light that is highly ordered. How can ordinary matter produce such perfectly organized radiation? The answer lies in one of the most remarkable phenomena in quantum physics: stimulated emission. The word laser stands for light amplification by stimulated emission of radiation. That phrase describes exactly what happens inside the device. Light is amplified through a quantum mechanical process. To understand this, we must look at atoms. Electrons inside atoms occupy discrete energy levels. They cannot exist between these levels. If energy is supplied, through electrical discharge, optical pumping, or chemical reactions, an electron can move to a higher energy state. If you like similar educational content, please like, subscribe, and share the video with your friends. This excited state is unstable. Eventually, the electron returns to a lower energy level and releases the excess energy as a photon. This is known as spontaneous emission. In conventional light sources, spontaneous emission dominates. Photons are emitted in random directions, with random phases and often across a range of wavelengths. A laser does not rely on randomness. If a photon of a specific energy interacts with an already excited atom, it can trigger that atom to emit a second photon that is identical to the first. Same wavelength, same direction, same phase, same polarization. This is stimulated emission. The result is two perfectly synchronized photons. If this process repeats thousands, millions, or billions of times, a cascade forms. The light becomes coherent, monochromatic, and highly directional. Laser light is therefore coherent, nearly single wavelength, extremely low in divergence. It is not simply bright light. It is quantum-controlled radiation. However, stimulated emission cannot dominate naturally. Under normal conditions, most atoms remain in their ground state. For a laser to operate, something extraordinary must occur: population inversion. Under normal thermal equilibrium, most atoms reside in their lowest energy state. Higher energy levels are sparsely populated because systems naturally minimize energy. In this condition, incoming photons are statistically more likely to be absorbed than to trigger stimulated emission. That means no amplification. For a laser to function, this balance must be reversed. There must be more atoms in an excited state than in the ground state. This unnatural condition is called population inversion. Population inversion is the absolute requirement for laser action. If population inversion is not achieved, stimulated emission cannot dominate absorption, and no sustained amplification occurs. How population inversion is created. The process of supplying energy to the laser medium is called pumping. Pumping methods vary depending on the type of laser. Electrical discharge, common in gas lasers. Optical pumping using flash lamps or other lasers. Direct electrical current injection in semiconductor lasers. Chemical reactions in high-energy systems. Goal is always the same: elevate a large number of electrons to higher energy levels. Many laser systems use metastable states. These are excited energy levels with unusually long lifetimes. Electrons remain there long enough for population inversion to build up. Without metastable states, excited electrons would decay too quickly, and inversion could not be sustained. The optical resonator controlling direction and amplification. Even with population inversion, spontaneous stimulated emission alone would not produce a usable beam. The emitted photons would still propagate in many directions. To control and amplify the radiation, the active medium is placed between two mirrors, forming an optical resonator. One mirror is almost perfectly reflective. The other is partially reflective. When a photon traveling along the axis of the resonator triggers stimulated emission, the newly generated photon travels in the same direction. The photons bounce back and forth between the mirrors, repeatedly passing through the excited medium. With every pass, more stimulated emission occurs. The number of coherent photons grows exponentially. This amplification continues until gain exceeds losses. Once the amplification reaches threshold, a portion of the coherent radiation exits through the partially reflective mirror, forming the laser beam. The optical resonator serves several critical functions. It enforces directionality, it selects specific wavelengths, it stabilizes phase coherence, it defines the spatial mode of the beam. Only photons traveling along specific paths and satisfying resonance conditions are amplified. The result is an extremely narrow, highly directional beam with minimal divergence. At this point, we have a functioning laser. Population inversion provides gain, and the resonator provides control. Although all lasers rely on stimulated emission, population inversion, and optical resonance, the properties of the laser beam depend heavily on the active medium. The material inside the resonator determines the wavelength of the emitted light, the achievable power, the efficiency, the cooling requirements, the practical applications. Let's examine the major categories. Solid-state lasers. Energy stored in a crystal. In solid-state lasers, the active medium is typically a crystal doped with specific ions. A classic example is the ruby laser, one of the first working laser systems. Modern systems often use neodymium-doped yttrium aluminum garnet. In these lasers, energy is delivered via optical pumping, often using flash lamps or laser diodes. The dopant ions absorb energy and transition to higher energy states. Because of metastable levels, population inversion can be achieved. Solid-state lasers are known for high peak power, excellent beam quality, strong industrial performance. They are widely used in metal cutting, welding, medical procedures, and precision manufacturing. However, they require efficient cooling because high-energy pumping generates significant heat. Gas lasers, excited atoms in plasma gas. Lasers use excited atoms or molecules in a gaseous state as the active medium. The helium-neon laser is one of the most recognizable examples, producing stable red light. In this system, helium atoms transfer energy to neon atoms through collisions. Another major category is the CO2 laser, which operates in the infrared range. CO2 lasers can achieve extremely high power and are commonly used for industrial cutting and engraving. Gas lasers are characterized by very stable wavelengths, high beam coherence, larger physical size, high voltage electrical requirements. Because gas lasers often operate at specific molecular transition frequencies, their wavelengths are extremely well defined. Semiconductor lasers. Compact quantum devices. The most widespread type of laser today is the semiconductor laser, also known as a laser diode. Instead of isolated atoms, these devices use electron-hole recombination in a p-n junction. When current flows through the junction, electrons and holes recombine, releasing energy as photons. Under the right conditions, stimulated emission dominates, and coherent light is generated. Semiconductor lasers are extremely compact, highly energy efficient, low cost, easily integrated into electronics. They are used in fiber optic communication, barcode scanners, laser printers, optical storage systems, medical devices. Their small size and scalability have made them foundational in modern digital infrastructure. Why do lasers have different colors? The wavelength of a laser depends on the energy difference between quantum states in the active medium. According to quantum mechanics, greater energy difference is equal to shorter wavelength. Smaller energy difference is equal to longer wavelength. This is why some lasers emit red light, others green or blue, and many operate in infrared or ultraviolet ranges invisible to the human eye. Laser emission is nearly monochromatic because the resonator selectively amplifies only very narrow spectral lines. By now we understand how lasers are generated and why different types exist. Now that we understand stimulated emission, population inversion, and resonator physics, we can step back and see the larger picture. The laser is not just a scientific curiosity. It is one of the most transformative technologies of the modern era. Its unique properties, coherence, monochromaticity, low divergence, and high energy density, allow energy to be delivered with extraordinary precision. Industrial applications. Controlled energy at extreme density. When a laser beam is focused to a small spot, the energy density becomes enormous. This allows materials to be cut welded, engraved, surface treated, additively manufactured. Unlike mechanical tools, a laser does not wear out from physical contact. The interaction is purely electromagnetic. In high-power industrial systems, lasers can melt or vaporize steel in fractions of a second. At lower power levels, they can engrave micrometer-scale patterns. Precision and repeatability are unmatched. Medical applications. Selective interaction with tissue. In medicine, the wavelength of the laser determines how it interacts with biological tissue. Different tissues absorb different wavelengths. For example, ophthalmic lasers reshape the cornea with micrometer precision. Dermatological lasers target pigment or blood vessels selectively. Surgical lasers allow controlled cutting with minimal bleeding. Because laser energy can be finely tuned in wavelength and pulse duration, it enables highly selective procedures. Ultra-short pulse lasers can even minimize thermal damage by confining energy deposition to extremely short timescales. Telecommunications light-carrying information. One of the most critical applications of lasers is in fiber optic communication. In optical fibers, data is transmitted as rapid sequences of light pulses. Because laser light is coherent and nearly monochromatic, it travels long distances with minimal dispersion and signal loss. Modern global internet infrastructure depends heavily on semiconductor laser diodes. Without lasers, high-speed global data transmission would not be possible at current scales. Scientific research. Exploring extreme physics. Lasers are also indispensable research tools. High-intensity lasers can create plasma states. Ultra-fast lasers can observe chemical reactions at femtosecond timescales. Precision laser interferometry can measure distances smaller than the diameter of a proton. Laser systems are used in atomic clocks, spectroscopy, particle acceleration fusion research. They allow scientists to manipulate and measure matter with extraordinary accuracy. Final understanding. A laser works because atoms are driven into population inversion. Stimulated emission produces identical photons. An optical resonator amplifies specific modes. Coherent radiation exits as a focused beam. It is controlled quantum amplification. Laser technology demonstrates how abstract principles of quantum mechanics can become practical tools that reshape industry, medicine, communication, and science. It is not merely a brighter light. It is engineered coherence, precision built from quantum rules.